So I think I should tell you this secret. There is a very important theorem called rearrangement theorem. Rearrangement theorem states that every row and every column of group multiplication table, I will shorthand write it this way, should have every group element once and only once. Okay, so this is called rearrangement theorem. So if I take a column, I should accommodate all elements at least once, and I should have only once. So this is a very powerful theorem which will allow me, now I know this and this I fixed, then here I cannot get B, so I should get C, here I cannot get C, I should get B. Okay, so this is the trick using which I wrote this. So this is satisfied by all group multiplication table. No, it's generally possible for all groups. Rearrangement theorem is possible for all groups. Even non-abelian case, rearrangement theorem is true.
Identifying the multiplication table.
No. Yeah, as the order increases, it is usually difficult if you do not know the elements. See, here I don't know what are these elements. If I define these elements as some numbers, then I can write group multiplication table by way of multiplying them. Or if I know what are those transformations, I can multiply them and write the group multiplication table. This exercise of asking a very general set to be a group is difficult as you go along higher and higher order groups. That I agree. And also, you might have noticed that all cyclic groups are abelian. Correct? Because a square a cube is same as a cube a square, it is a power 5. So all cyclic groups are abelian. Okay? So that is an additional remark. It's very obvious, but still I just, for completeness sake, I made that remark. So now if you see, this is different from cyclic group. Now what happens in this case, you have, so in this particular case, I cannot say there is only one generator. How many generators are there? An element is called a generator if some power of it is equal to identity. Here we have 3 generators. What is the order of A? 2. A square is identity. Order of B is also 2. Order of C is also 2. So in this group, we have 3 generators, A, B and C. So order of A is equal to 2, order of C is also equal to 2. So this is not a cyclic group. Okay, it is a group which has 3 generators, and none of the order of these generators is order of the group, because that if order of the group is equal to order of the generator, then that will become a cyclic group. So this is a non-cyclic group. Non-cyclic group. But you can notice this group is also abelian. This group is also abelian. So we have order 1, only cyclic group possible. Order 2, only cyclic group is possible. Order 3, only cyclic group is possible. Order 4, a non-cyclic group is possible, but that's also abelian. Order 5, once again only cyclic group is possible. So the first non-abelian group has an order 6. You cannot have a non-abelian group with order less than 6. Okay? So a general rule can be said that all groups of order less than 6 are abelian. You may have a group of order more than 6, that is also abelian, but the first non-abelian group is of the order of 6. Okay? So this is the construction of groups with different orders. As I told you, if you want to write E, A, B, C, D, okay, it turns out that that's only cyclic group is possible for that. We will see why after we define some more concepts of subgroups and things like that. And if you have 5, 6, 7, the conditions become more and more complicated, and such a general classification is not very easy. Now, after getting kind of a hang on the definition of a group, let us try to classify these groups based on the order. Okay? So, generally groups can be divided into two categories. One category I will call it as discrete groups, and the other category continuous groups. Discrete groups and continuous groups. Within the discrete groups, I can further categorize finite groups and infinite groups. Continuous groups can also be categorized into two further categories: compact groups and non-compact groups. Okay, so this is a general classification of the groups that we come across in the whole of this group theory. Finite groups have got the order of the group to be finite number, 10, 15, it may be 1000, but it's finite. Infinite group, order of the group is infinite. Order of the group is always infinite for continuous groups, but here you have two categories, compact and non-compact groups. Let's look at examples of each category. Supposing I have G is equal to 1, 2, 3, 4, and the operation is multiplication modulo 5. Multiplication modulo 5. What is this operation meaning? If I multiply 3 with 3, I will get 9. But 9 is not an element of this set. But when I say 9 modulo 5, I must divide 9 by 5 and take the remainder, whatever is the remainder. It will not divide it, but you will have a remainder, right? That remainder is what is the answer. So 9 means, what should that element be? 4. 4 into 4 is 16. What is that element? 1, because 16 minus 15 is 1. So this is an example of which category? Finite group, because order of the group is 4. So what is the multiplication table of this? 1, 2, 3, 4, 1, 2, 3, 4, and this is multiplication modulo 5. 1 is the identity, so this is same, this is same. And what is 2 into 2? 1. 2 into 4? 3 into 2? 3 into 3? 3 into 4? This is 4. 4 into 2 is 3. 4 into 3 is 2. 4 into 4 is 1. Is this a cyclic group? We have actually two conditions for a 4-element set to be a group. One is cyclic group. The other is the group which we just discussed with the 3 generators. Each one is its own inverse. Correct? Is it like that? 2, 2 is not identity. So this has to be cyclic. These are the only two conditions. Up to 3-element group, only one condition. For 4-element group, there are two conditions. And this is a cyclic group. It is not self-inverse, so it has to be cyclic. So 2 is a generator. 2 square is 4. 2 cube is 3. 2 power 4 is 1. So it is a cyclic group. Generator is 2 and order of 2 is equal to 4, which is equal to the order of the group. Let us consider G as set of all integers, and the binary composition law is usual addition. Is this a group? Is this group an abelian group? You don't have to check, because I told you every group less than 6 is an abelian group. So is this a group? How do we check whether it's a group? You have to go back and satisfy all the axioms. Here we could write multiplication table, but what is the order of this group if it's a group? Infinity. But it's a discrete group, because between 1 and 2 there are no elements. There are infinitely many elements, but there are denumerable or countable. So it is a discrete group, but it is an infinite group. What is the identity here? 0 is the identity. Okay. So in this group, identity is usual 0. Now for every m in Z, we have m inverse. What is m inverse? What is m inverse? Minus m. Is it an abelian group? Huh? Is it an abelian or non-abelian? Why? Still it is an abelian group. You take any negative number, add a positive number, or positive number, add a negative number, you will get the same, right? So this is an abelian group. So Z plus is an abelian group. This is an example for discrete group of infinite order. Order of this group is infinite. Now take another example.